Now, the last thing that we need to do with our look at the structure of matter is deal with Feynman diagrams. And Feynman diagrams are diagrams representing particle interactions. Now, there are a few sort of conventions or aspects about them that we need to identify. If you don't really know what you're looking at with Feynman diagrams, then it's all just going to be a bit of a mess. So we need to talk about some of the features that you'll see. So the first thing is that in representing a particle, we actually represent it with an arrow with or a straight line with an arrow. So that represents a particle of some type. Usually we'd label the particle, so let's say it was a proton, we'd put a P there beside it. If it was a pion, then we'd put a pi next to it. So that indicates the type of particle. Now, an antiparticle, we still use a straight line, but the arrow is in the opposite direction. I'll come back and talk about that in a bit more detail when we look at the diagram as a whole. But ultimately, the antiparticle, sort of the arrow points in the opposite direction. Now, the other thing that we can indicate with on Feynman diagrams, or the other things we have to indicate, are the exchange particles, and we use two different types of representations usually for the particle interactions. And so for the exchange particles, we're usually going to use a dashed line for the W minus, W plus, and Z neutral, and then a squiggle line for photons. So these represent the exchange particles. Now, with the Feynman diagrams that we're going to look at, we're generally going to be dealing with gauge bosons, but sometimes you can actually have other particles that act as the exchange particle. You'll notice that we've left out gluons there. We will sort of deal with those as we need to as we go along, but mostly we'll be dealing with the those W minus, W plus, Z naught, and gamma. Now, when we represent interactions of particles, there's a few things to be aware of. The first thing is that we're dealing with, we'll always deal with a vertex. So if we look at a vertex, we're going to have three lines joining it. So it'll be something like that. So this point here is the vertex. Now, this line that's going in would be an incoming particle, and the one that's going out would be the outgoing particle. Now, for an interaction, we're actually going to need to have two vertices, but ultimately, at a vertex, we need to make sure we've got an incoming, an outgoing, and an exchange particle. The other thing that's really important to note is that as we go up, so if you think about the vertical axis here, that represents the time axis. As we go across, we're representing space or position. So it's not really an idea of what the displacement is. It's more just that we're looking at it being space and time is what we're dealing with. Now, at a vertex, some important rules need to apply. So at a vertex, we have that charge, lepton number, and baryon number are all conserved. So we can figure out certain particles that are going to be involved or produced, or what the exchange particle will be, by making sure that we balance the charge, lepton number, and baryon number. Now, instead of sort of going through more and more details, we're going to have a look at some specific examples now. And to begin with, the first one, you might sort of think this is a bit silly, but it helps to just sort of get your head around how to represent these interactions. So the first one is just going to be electron repulsion. So in this particular case, we're going to have an electron on this side, and we'll have an electron coming in on the other side as well. And the particle that's going to mediate the interaction here is a photon. In this case, it's actually a virtual photon. And the reason why we say that it's a virtual photon is that we don't actually see it. We can't detect it during the exchange that's going on. And as a result, because we can't detect it, it's referred to as being a virtual photon. So virtual particles, basically, we can't detect them, and if we could detect them, then they're not actually mediating the force. So virtual photon that exists between the two. And what we would expect to see there, and what we in fact do see, is that those two electrons would then be repelled, and as a result they would continue moving on, having been repelled from each other. So there's the first fairly straightforward example. The second example we're going to look at is one that we've referred to a few times now, and that's the decay of a photon, decay of a neutron. So with the decay of a neutron, that's the process that we see in beta decay. And I'll just rewrite the equation here again just to refresh your memory. So a neutron turns into a proton, an electron, and an electron antineutrino. So in this interaction, we're going to see that the neutron is basically the only particle going into the interaction, and as a result we get a proton being produced. Now you can see here that if we've got the neutron going in with a charge of 0 and the proton coming out with a charge of +1, it must mean that we have an exchange particle here that is negative, so that we balance the charge at this particular vertex. And because it's a decay, it would be the weak force that's involved, and so we'd see that it's a W boson, W negative. On the other side, we then have two particles being produced, being the electron and the electron antineutrino. Now you recall, as I said before, we have to represent antiparticles with the arrow going in the opposite direction. That doesn't mean that it's travelling backwards through time, it's just to indicate very clearly that it's an antiparticle. So anytime we have an antiparticle, the arrow will look like it's going down, look like it's going backwards through time. It's actually just to indicate that it's an antiparticle. It's not actually about the fact which direction through time it's travelling. The last example then is an electron-positron annihilation. So you'll recall that if we have a particle and its antiparticle, if they collide, then they will annihilate each other, and so we can show that in a Feynman diagram. And in this case, we'll have the electron travelling in, and the positron travelling in, again positron being the antiparticle. So we represent that with the downwards facing arrow. In this case we know that we'll see two photons being produced. So notice in this case they're not virtual photons, we actually do see them. So the squiggly lines there represent the photons themselves. Again though, we've got a negative particle going in and a gamma ray that has no charge coming back out. So this particle that we see across here is actually just represented using the electron itself. So the electron is kind of the exchange particle in this interaction between the positron and the electron. And as a result we see the two gamma ray photons being produced. So you can see the few examples there. We've always got particles coming in, we've always got particles going out, and then we have the exchange particle that mediates the interaction between those two. There are a few more questions that we'll go through in class along these lines. A few things to wrap your mind around there to make sure you understand what these interactions involve and how to interpret them, how to figure out what might be missing as well.